Hello everybody, welcome to our lesson. Today's topic is self-induction and inductance. This is the goal of the lesson. At the end of the lesson you will be able to define the self-induction and inductance, write induced EMF in terms of inductance, and derive the inductance for a solenoid. Well, consider a circuit consisting of a switch, a battery, a source of EMF, bulb, and a straight wire. So here, when I close and open the switch, the bulb immediately lights and shuts. And then I wound a piece of wire, making it a coil. Now, here is the most interesting thing happens. When I close the switch, the bulb doesn't light immediately. It starts from dim light and only by time gets brighter and brighter. And when I open the switch, light from the bulb doesn't disappear immediately. Even if there is no connection with the battery, the bulb continues to produce light. And this is weird. And only after a few seconds, the bulb stops shining. Well, to have a better analysis, I will replace the bulb to an ammeter and will perform the same action for both situations. And I'm going to record readings of an ammeter and plot it in a graph. The graph will show the current to time dependence. Okay, let's close the switch for both situations and observe what happens here. So, as you see from the graph, the current with the wire in the first situation takes its maximum value in a very short interval of time, while the current with the coil in the second situation is only at its beginning. And current here didn't immediately jump from 0 to its maximum value. It took a few seconds more to do that. You can observe it from the graph. Note the time for the first situation to increase its current to maximum and the time at the second situation to increase current for maximum. And if I open the switch and disconnect the circuit from a battery, the current in the second scenario also doesn't jump from maximum value to 0. It decreases gradually, we see it from the graph, while the current in the first situation jumps from maximum to 0 instantly. So we see some weird thing here. In the first situation, when I have a wire, a straight wire, when I close and open the switch, current jumped to 0, from 0 to maximum immediately, and also from maximum value to 0 immediately. But if I wound this straight wire and make it a coil, we see here in this situation current increases slowly to its maximum value, also decreases slowly to its minimum value. And the weird thing is, even if there is no connection with the battery, we have still a current. And how can we explain this phenomenon? Okay, to do this, let's discuss the second situation with a coil in details. As the current increases with time, we know the magnetic field lines surrounding the wires pass through the loop represented by the circuit itself. This magnetic field passing through the loop causes magnetic flux through the loop. And we know from Faraday's law of induction, this increasing flux creates an induced EMF in the circuit. And from the Lenz's law, the direction of the induced EMF is opposing the change in the magnetic flux. Therefore, the direction of the induced EMF is opposite the direction of the EMF of the battery. So this is the reason why we have a gradual increase rather than instantaneous decrease. And this is the reason why current is taking its maximum value slowly. And if the switch is open, the direction of the induced EMF sets up the same direction with the EMF of the battery, which causes current to flow even if there is no connection with the battery. So simply, this coil at first situation, when current increases through the coil, it resists to this increase, and that's why we have a slow increase in the current. But the most interesting thing, if there is no connection with the battery and the current decreases through this loop, and here the loop starts to resist that decrease, and it sets up an EMF that will circulate the current through the loop even if there is no connection with the battery. So simply, at the second situation, the coil here, at first when current increases, it acts like a resistor, it resists the current, and if the current decreases, it acts like a battery. That's the most interesting thing. And this effect is called self-induction, because the changing flux through the circuit and the resultant induced EMF arise from the circuit itself. The EMF set up in this case is called a self-induced EMF. And the American physicist Henry discovered the phenomenon of self-induction, but unfortunately he failed to publish his findings. Okay, now let's try to derive an equation for a self-induced EMF. So to do this, consider the solenoid given in the picture, which has a length of L, cross-sectional area of A, and number of turns N. Initially, current through the solenoid is I1 and the magnetic field is B0. And the current in the second situation increases. So, as a result of increasing current, the magnetic flux through the solenoid increases. Hence, the magnetic field increases. And we know from the Faraday's law, if there is an increase in flux, self-induced EMF produced, which opposes the change of a current. And the magnetic field produced by a solenoid is calculated using these equations. So this is the equation from the previous lessons. This is the field at the center of a solenoid, and it's calculated by multiplying μ0, its permeability of free space, and its turns density, its number of turns per length of the solenoid, and I1 its current. And here we have found the magnetic field at the second situation. It's μ0 and I2. And we can calculate the flux through the loop by multiplying field to an area. So if we replace this expression into the equation for the flux, we have for the flux 1 μ0 and I1A, and for the flux 2 μ0 and I2A. Then we find the change in magnetic flux. So change in flux, it's flux 2 minus flux 1. And this is μ0 times N times A, I2 minus I1. And I2 minus I1, it's the change in current. So we can write in this form. Change in flux is μ0 times N times area times change in current. So we put the expression for delta phi, the changing flux, into Faraday's equation for induction. And for convenience, let's write delta I over delta T separately. You see here. So what we did here, we've replaced the expression found for the change in flux here. This is μ0 and A delta I. And I'm going to write delta I over delta T separately. So here's some constant we see, N, μ0, N, and A. And we have a rate of current delta I over delta T here. And N here, it's the turns density of a coil and can be found as the number of loops over the length of the solenoid. So this is the turns density, it is number of loop over L, and we can find also number of loops here by multiplying turns density to the length. So here this equation can be changed as follows. We replace N by the small n times L. And here we see that we have N here and one more N here. It's N times N squared, and we can write it in this form. Minus mu0 N squared A times L. And what is A times L? It is the area times the length of the solenoid. So basically it's the volume of the solenoid. So we see this kind of expression here now. The induced EMF, the self-induced EMF, is equals to minus mu0 times N squared times V delta I over delta T. As we said, mu0 is the constant, it's permeability of free space, N it's turns density, V it's volume, this is change in current, this is change in time. So the EMF, as we said, is this times this, and this is some constant, and we call this inductance of a solenoid. So the self-induced of EMF of any coil can be found as follows, and this equation can be applied not only to a coil but any type of conductors. The minus sign in this expression is the Lenz's law, indicating that the EMF opposes to the change in current. One important point to note about the above equation, it only relates the EMF produced across the inductor to change in current, because if the flow of current is constant and not changing, then the induced EMF voltage will be zero. So now let's discuss the inductance of a coil. The L here, it's the inductance. Let's discuss this. We have observed that the coil resists to any change of current when connected to a circuit, but it will easily pass a steady current. The ability of a coil of wire to resist change in current is called inductance. So inductance is a property of a coil, it's the property of a coil to resist any change in current. So the unit of inductance can be calculated using this equation. If we ignore the minus sign, the inductance is equal to EMF over delta I over delta T. So this is from this equation. We can ignore the minus because it doesn't affect to the unit. So let's write the units for the EMF. It is volt, and for the current it is ampere, and for the time it is second. So the unit for the inductance is volt over ampere over second. And physicists gave this unit a special name, Henry, in honor of American physicist Henry. And we can say in International System of Units, the unit for the inductance is Henry. And now we will talk about the parameters that affect the inductance of a conductor. So we will start from what we have already found. This is the expression for an inductance of a solenoid. And we see from this expression that inductance, the property of resisting to a change in current, depends on physical properties. So inductance depends on what? It depends on how tightly the wires are wound, it's the turns density, and the inductance also depends on the size of the solenoid, to the volume of the solenoid. And inductance also depends on the magnetic permeability. Here, because of a vacuum, we have a permeability of a free space. But if the coil is wound around an iron coil, then the inductance is increased by the relative permeability of the material. So, inductance depends on three things. On the material which coil is wound, it is relative permeability, and on the way how tight the wires are wound, it's the turns density, and inductance depends also on the size of a solenoid. It is volume. And how can we find inductance for any conductors, not only for solenoid? To do this, we will use these equations, Faraday's law and the equation for the self-induced EMF, which we have found today. So this equation both is about EMF, and we can equalize these equations. So N delta F over delta T is equals to L delta I over delta T. And here we see that time can be cancelled out. So we have N times delta F times L times delta I. So also we can say this: if this expression is true for the change in flux and change in current, then this expression is true for any instant. So that's why N times F is equals to L times I. And we have an equation for the inductance of every conductor. So to find an inductance not only for a solenoid, we multiply number of turns to the flux and divide by current. Well, this is the end of the lesson. I hope you've enjoyed our lesson. Please subscribe and share.